Up to this point, we've used PIC24 timers for generating periodic interrupts. Let's examine some other applications for timers. The input capture and output compare modules are peripherals that use timer 2 or timer 3 for time-related functions. The output compare module can generate pulses of a specific pulse width and period. The input capture module is used for measuring pulse width and period. The output compare module is used to generate pulses of a specific width on a pin that we're going to call the output compare pin. In order to do this, we need to be able to control the duration of both the high and the low pulse widths. Now, we have generated waveforms like this in previous examples by using a periodic interrupt that toggled an output pin. However, the goal of the output compare module is to generate these waveforms with more flexibility, more accuracy, and more stability. Note that the basic element driving this output is a set reset flip-flop. When the pin is to be set high, the set input will be asserted. When the pin is to be set low, the R input, the reset input, will be asserted. This output logic is going to determine when and how this set reset pins are going to be asserted, and it's going to be based upon two things. One is going to be a mode select that's going to determine what mode we're operating in. Is it going to be a continuous pulse? Is it going to be one-shot pulses, etc.? And then we need to know when to do it, and that's going to be provided by this comparator input that is going to compare either a timer 2 or timer 3 value against a special function register that we're going to call the OCR register. Note that the output compare module must work with either timer 2 or timer 3. It does not have a built-in timer itself, so it will be dependent upon one of these two timer subsystems. Let's talk about the various output compare modes. The first thing we'll talk about is the one-shot modes. We'll talk about the active high one-shot mode, since the active low one-shot mode functions exactly the same as the active high, except that the voltage levels are reversed. Initially, the output compare pin will be low. It will go high whenever you write this mode value to the output compare control register. When you do that, the output compare pin will go to a high, and it will remain a high until the value in the output compare register matches either the timer 2 or timer 3 timer value, whichever one has been selected. When that match happens, the output pin will be reset back to its idle state, and it will remain in its idle state of low until you trigger the one shot again by rewriting these bits to the output compare control register. The toggle mode simply toggles this output pin each time a match occurs between the OCR register and the selected either timer 2 or timer 3 value. Notice that this high pulse width and this low pulse will be equal to each other as long as the period register that's being used to the timer remains a constant. The delayed one-shot mode uses the second register here, the OCRS register, in addition to the OCR register. It will go to a high whenever the timer value matches the value in the OCR register, and then the pin will return low whenever the OCRS register value matches the timer value. So the pulse width here will be the difference between these two register values. A continuous pulse mode operates the same as a delayed one-shot, except it continually puts out these pulses instead of putting out only one pulse. The pulse width modulation mode, or PWM for short, works as follows. Whenever the mode is initially enabled, the output pin will go high. The output pin will then return low when the OCR register value matches the selected timer value. At that point, the pin will remain low until the timer is reset on period match, at which point it will return high, and then the process repeats. Notice that this period of this PWM waveform is going to be set by the timer period, while the pulse width value, the pulse width time, is going to be proportional to the OCR register value. Let's use the output compare module and the toggle mode to generate a square wave. We're going to use timer 2 as the base timer for this output compare module, and we'll configure it for a period that will be greater than 1/2 the period of square wave. We'll initialize the OCR register to the number of timer ticks for 1/2 of the square wave period. Then each time this OCR register matches, it's going to generate an OC1 interrupt, and in that OC1 ISR, we're going to assign a new OCR register value that's going to be the current value plus a number of timer ticks that's 1/2 the square wave period. So let's look at some code that implements the method on the previous slide to use the output compare module to create a square wave. So first thing we'll do is we'll config basic like we always do. Then we're going to config timer 2. We're going to not show all the details of this code since we've done that in previous lectures. We're going to use a prescale of 64. No interrupt will be required. We're going to set the PR2 to its maximum value. With these settings, we're going to get a period of about 105 milliseconds. This is much greater than our square wave half period that we want to generate of 2500 microseconds or 2.5 milliseconds. What this means is that we could lower this prescale down to the next lower value, which is 8, and get a bit more accuracy on this square wave, but for this example we use a prescale of 64. After timer 2 is configured, the next thing we're going to do is configure the output compare module. That's going to be done by this code here. The first thing we do is going to disable the timer. The datasheet says that when writing the output compare control module for correct operation, the timer should be disabled. So that's what we're going to do. We're going to take the OC1 pin and we're going to map that to remappable pin 2. So that means that our square wave is going to appear on remappable pin RP2. At that point, we then want to compute for our desired square wave half period in microseconds. We want to take that and convert it to the number of ticks required to generate that number of microseconds. So we'll do that using this function, microseconds to use 16 ticks, and we'll save it in this variable. We're then going to initialize our OCR register to this variable, to this value, which is going to be the length of a half period in timer ticks. We're then going to configure our output compare control register. We're going to choose timer 2 as our source timer, and we're going to use the toggle mode. We then need to enable our OC output compare interrupt, so we'll clear the flag, we'll set a priority higher than 0, and we'll enable it. What is this ISR going to do? Well, the ISR, which is here, is going to be called when the timer matches the OCR register. When that occurs, we're going to clear the interrupt flag, and then we're going to add to the current OCR register value this number of ticks that's equal to 1/2 of a period, and write that back to the OCR register. So this number of ticks in the future, we will get another OC1 interrupt, and we'll update it again. Each time that we get this match of the OCR register with the timer, the output pin is going to be toggled by the output compare hardware. Once the output compare module has been configured, we're then going to turn on the timer. At that point, the timer will start clicking. We will enter an infinite loop, and we'll do nothing here because the output compare module hardware is going to be doing all of the work. Once the timer matches the output compare OCR register, then, as we said before, the pin will be toggled. We'll enter the ISR, clear the flag, update our OCR register with this value here, which is to cause another interrupt, this number of ticks in the future, and this will just keep doing this, toggling the pin each interrupt and generating a square wave. Recall that back in chapter 9, we had an example in which we used timer 2 to generate a square wave by generating a periodic interrupt every 15 milliseconds, and then inside the ISR we simply toggled an output pin. If we can generate a square wave this way, why do we even need the output compare module method of generating a square wave? Well, the problem with this method is there are a couple of problems. One, whenever an interrupt occurs, there's some uncertainty as to how many clock cycles it will actually take to enter this interrupt based upon where in the instruction cycle the interrupt occurs. The other thing that could happen is that if there was a higher priority interrupt occurring and currently executing, then this square wave right here, the interrupt may be delayed because the higher priority interrupt was currently executing. All of those two things would cause the output square wave to have some jitter in it. And what jitter means is that these edges here would move around a little bit. The frequency would not be fixed. It'd be changing slightly. And so jitter is something that we would like to avoid on a square wave. Using the output compare module to generate a square wave is going to help us avoid the jitter problems of the previous method. The jitter problems of the previous method occurred because of uncertainty in the number of clock cycles it took to enter this ISR once the interrupt occurred. That uncertainty could happen because either a higher priority interrupt was executing or because of where the interrupt occurred in the clock cycle of an instruction. So what this approach does is going to help give us more room for uncertainty, and it does that because it is actually not toggling the pin in the ISR. The pin is being toggled by the OCR hardware itself when that match occurs between the OCR register and the timer. Once we enter this ISR, our only job is to update this OCR register with this new value. As long as we do that before this number of ticks has elapsed, then we're going to get a jitter-free square wave.